Hello, my name is Robin Mitchell and welcome to this podcast for Electropages. In today's episode, we're going to be talking to the CEO of Agile Analog to find out the challenges that engineers face when it comes to choosing analog IP, what the company does, and how its solutions can help engineers. Right, well, thank you for joining us on this podcast today, and I would like you to start by introducing yourself, who you are, and what it is you do.
Hi, Robin. It's good to meet with you today. My name is Barry Paterson. I'm the CEO of Agile Analog, which is an analog IP company based in Cambridge in the UK.
And so, in terms of the products that you actually sell to customers and engineers, how is it? What is it that you actually do then?
So what we do is we license analog IP cores that our customers then integrate into their system on chip products. So we're part of the semiconductor design ecosystem, where we develop particular functions and features that are required to build analog interfaces, essentially, between the digital world and the analog world.
And so what industries do your customers tend to be in then?
So our customers tend to be across the whole spectrum of, consumer electronics, automotive, space military, basically anywhere where semiconductors are used. What we're finding is that there are more and more companies now beginning to do their own custom silicon. And for them, being able to access IP is really something that helps them get their custom silicon to market faster. We also find there are a number of digital companies, SoC companies, that are developing large-scale digital components that do actually now need to integrate in analog functionality for things like sensor interfaces, etc. And for them, they have no ecosystem or no methodologies and flows for analog design. And so the ability to actually pick up an analog IP core and simply integrate it in is of huge value to them.
And so would it be right to say that in terms of the IP world, when it comes to custom silicon, that the analog area is kind of lacking in comparison to like the digital realm?
It is. One of the big challenges in the analog domain is that analog really puts a constraint on digital. At the moment with digital, you've actually managed to abstract the design into, Verilog, system Verilog, VHDL, etc. So there's a hardware description language, which basically means that you can, through logic synthesis, retarget that into any process node. Not so much with analog. Analog tends to be hand-built, a very specific implementation on a very specific process, and therefore you don't have that agility, if you like, to move from one foundry to another, or from one process node to another. And every analog IP core tends to be a bespoke design for a particular process node. Our proposition is that we've found a way to automate that such that we can offer that agility to customers, so that if a customer is looking for an analog core in a particular process that suits their system on chip design, we will be able to produce that analog IP for them very, very quickly, because internally with the Agile Analog, we've developed a technology that allows us to automate the analog design.
It's really interesting you mentioned about the bespokeness of analog design, and I suppose it never really occurred to me, but it actually makes sense when you think about it. So take, for example, digital circuits. It's just transistors which switch on and off, so you don't really care how they're switching or the properties of that transistor. But when it comes to analog design, what you're saying is that if you're building a resistor, a capacitor, or an inductor into a piece of silicon, that the thickness of the oxide layer is going to make differences in terms of its characteristics. The conductivity of the silicon will also change how those components sort of operate. And so it obviously introduces, like you're saying, it introduces a lot of challenges for engineers when they're trying to create a unique analog circuit which is based on the physical characteristics of the process which they're choosing, depending on the manufacturer.
That's absolutely correct. I mean, if you think about digital circuitry, it's literally transistors that are used as switches. So everything's either 1 or a 0. It all breaks down into Boolean logic. You can very quickly, build up a functionality and a feature set with that. With analog, it's a linear process. And so you're looking at the tolerancing of each transistor. You're looking at the variability of each process. You're looking at the number of transistors, capacitors, resistors that are available in that process and what those characteristics will be across process voltage and temperature. And what the analog engineer needs to do is to make sure that their circuit will operate to a spec within that complete spectrum of process voltage and temperature. And, subtleties in a change in resistance or capacitance can mean, a huge difference on the output of an analog cell. And so really it takes a lot longer to go through this process of designing functionality, then looking at the performance, and then refining that performance over multiple iterations until you get it within the sweet spot of operation for that particular PDK. And then, when you actually go into manufacture, you've got all the variability of the manufacturing process, because you are talking about, process variation depending on how each individual wafer lot goes through the fab. And so the foundries then have to provide the PDK such that there's a tolerance for every transistor, every resistor, every capacitor. And you need to design within those tolerances to guarantee that you've got yield and that you've got performance across the full spectrum of that variability.
And so that variability is what essentially makes the analog IP sort of industry extremely complex by comparison to the digital realm.
It does. It means that trying to automate that is incredibly difficult, because you have to look at each PDK on its own, and you then have to look at each element of that PDK, and you need to understand what the variability of it is, and then use that as part of your construct for building the IP core. And so, there's layers of complexity upon complexity to allow you to do that, which makes it really challenging.
And so on the topic of the custom silicon industry, because things like RISC-V, that's all coming up, and that's becoming a really large market now. Do you expect that going forward into the future, engineers are going to be focusing more on custom semiconductors, and as a result, companies such as yourselves will become more important in those designs?
I think so. I mean, when you look at what's happening with ARM, what's happening with RISC-V, these are really processors that people are licensing their IP cores, and then they're building SoCs around those. In order for you to build an SoC, you probably do need to have some form of analog infrastructure there. For data conversion, for example, for data digital to analog converters, analog to digital converters, and you also maybe need to have some kind of power management. And then there's fundamental basic building blocks that you would need in the analog domain as well to give you like a very stable voltage reference, for example. And so what customers who are using RISC-V are doing is they're licensing IP for the digital part, but they're now also looking to license the IP for the analog functionality feature set they need. So we are actually a member of the RISC-V community. And one of the things that we're actively doing at the moment is building what we call subsystems. And these are complete analog solutions that will integrate easily into a RISC-V type of design and allow customers to develop things like sensor interfaces or always-on blocks, etc., which will enable them to build greater functionality into their SoCs.
So does that mean that the contribution which you're providing to the RISC-V Foundation, is it kind of a almost like a standardization, like building blocks, analog building block units, so that if, let's say, you're building a new RISC-V microcontroller, instead of having to try and redesign all of the analog infrastructure from scratch, your contribution might be that we've created a kind of like a standardized interface, so those making RISC-V microcontrollers can always interface with those interfaces. If that makes sense.
So there's two things we offer there. We can either do fully customized IP development, which will be to the process that the customer's using, and it will be the IP blocks they've identified that they need. Or, we will have subsystems which are, pre-designed system level solutions that customers can simply integrate into the RISC-V designs. What we're also doing is we're looking at how you would actually do that integration into a RISC-V type of design. And so we've developed a sort of class of our IP which is wrapped in digital. So from an integrator's perspective, it looks like a digital block, which makes it much easier to integrate it in. It means that it will fit into their design methodology and flow for things like verification and layout in a much more simplistic way. And it will make it easier to integrate analog functionality into a predominantly digital SoC. So, we can offer a kind of bespoke, you pick and choose which IPs you want, or we will have a number of pre-built solutions that customers can simply integrate.
And it's also quite funny as well how everyone in the past was always, everything's going to go digital, analog's going to go in the past. But, when you actually look at the future, you realize that analog hasn't been more important than it is today. Without analog electronics, you cannot do anything in the digital realm. And so it's quite interesting to see how, like you mentioned before, the analog industry has sort of been not kept behind, but it hasn't advanced as quickly as the digital industry. But the digital industry is so reliant on the analog industry.
Yeah, absolutely. It's an analog world. I mean, you think of the five senses, right? And they're all analog inputs of some form. You think about, some of the kind of trends in consumer electronics, things like smartwatches that have heart rate monitors, that have, blood oxygen meters, that, these are all analog functions that need to be somehow integrated into that overall system solution. Audio is another hugely analog domain as well. And then you've got things like, haptics, etc., for touch, that are important, and displays, etc., are also analog in nature. What's happened in the past is that there's been a segment of the market which is discrete analog. So you always had to have a big processor and a bunch of discrete analog around about that to support it. For some of the form factors we've got now, miniaturization and making things smaller and more integrated is the only way that you can move forward. And so you get this integration, de-integration cycle that tends to happen within the mixed signal world, where you basically start with the analog being a completely separate chip, and then you have a highly integrated digital solution. And at some point then the analog catches up in terms of being available in that process technology, and you integrate everything in together into a complex mixed signal chip. And then the digital moves forward. Moore's law continues on, and so you get higher levels of integration, lower power, higher density, and then the analog's left behind. So you go through a de-integration cycle. And so, throughout my career, I've seen this integration, de-integration cycle happen several times, because the analog part is always one step behind the digital. It can't keep up with the ability to move as quickly, because digital is just resynthesis. And so, for us at Agile Analog, part of that is if we can somehow have that continuous integration of analog with digital, then there's huge value in that. It really enables, analog to be continuously integrated into the digital, and it stops this delay and the constraint that you have of having to handcraft the analog core every time you want to move forward a technology node. And so really that's the proposition that we have, is that we now believe we can make the analog IP as agile as the digital.
And so that's a really interesting point you mentioned, which is that if when they release a new processor node and you've designed a processor, and the question is how do we make it more complex, make the transistor smaller, and then we can add more transistors, we can make more digital circuits integrated into a single package. And all of that is usually described in a hardware description language anyway. But like you say, with analog, it's, we've got a new processor node, and the question is, right, so how do we make it smaller? Right, back to the drawing board. It's right back to square one, because everything's now changed.
Correct. And not only that, but what you also find is that at these super advanced nodes is it takes a few years for those to stabilize. As you run, as the foundries run more material through the factory, they get a better understanding of exactly what that process performance is and what the process spread is. And so you might start a design for one of the advanced nodes in the analog domain, and then the foundry will come up with a PDK update. And it basically means that you have to scrap your design and start again, or you have to make significant modifications to it because they've updated the PDK, they've updated the transistor models. Again, if you have a level of automation, how you generate those transistors, which is what we have in Agile Analog, then it means that you can cope with PDK updates, you can cope with changes in the process technology and the transistor models as those are released by the foundries.
And thus the crux of what Agile Analog is trying to do is basically take analog circuits and give them the conveniences of digital design, essentially.
Essentially, yes. It's to make our analog IP process agnostic. That's the ultimate aim. So we have a number of IP products today that we're licensing to customers, and for some of the core IPs that we have available, we can generate those in any PDK that we have access to. And so that's our offering, is that, if you want them done in a specific foundry's PDK, then we will be able to do that far quicker than you can do it by hand. And because it's an automated flow, that means we will run consistent verification on those, so the quality of what we're delivering will be better than probably what you'll do internally because you may cut corners.
Well, that was absolutely fantastic, and it was great to get some insight into the world of analog semiconductor design. And thank you for taking the time to see us today. Thank you.
Very welcome, Robin. Thank you very much for the opportunity to discuss this with you.
So if you find this kind of content interesting and want to stay up to date with the latest news and trends in the industry, then go ahead and sign up to our newsletter, which can be found on the Electropages website, as well as a link in the description below. And if you want to support this channel, then also consider subscribing. Thank you for watching, and I'll see you next time.